All right, let's get this show on the road. Hello, everyone. Hope you're well. And have a few people missing, but I guess they'll join us in a bit. Let's just actually begin. So hopefully that quiz was okay. Slightly different format from the quiz last week. So one of the complaints about the quiz last week is just you didn't have enough time to scan everything and do all that. So I decided to do away with that. And because your final exam is going to be multiple choice, I figured, hey, maybe I can get them used to the whole multiple choice way of doing things with the quizzes. So again, I am really interested in seeing how you guys write things out as well. And I'll try to find a way to incorporate that at some other point. But I think for the time being, this format with the quizzes would be better. And it seems like so far most people prefer that. I think it's a good way to practice quizzes at least. And yes, especially since the fine is going to be in the same. And it prevents all the technical issues that can happen from scanning and, oh, I didn't have enough time and blah, 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 blah. So hopefully that quiz was better. And I think for the most part, future quizzes are going to be like that. So just trying a few things. So yes, last week's quiz was a trial run. We're all learning here. I'll be dropping a quiz, so I guess we'll drop last week's quiz if you really didn't do well on it or you didn't get to fulfill all the requirements. And hopefully moving forward, things will be a lot smoother. That being said, we are going to continue. So we don't have, we already used up a decent amount of today's class on the quiz, which is okay, but let's right now jump right into it. Hopefully you noticed that there were two bonus problems. So while your quiz on Gradescope says it was out of 14 points, technically it's out of 12. The last two were actually bonus points. I'm not sure what 8.6 and 8.7 is. I don't know what they are by the numbers. We are skipping one section, but we will come back to it. So we're going to do improper integrals. I skipped over approximate integration, numerical integration. We'll go back to that. I just feel like the flow is nicer if I go and do improper integrals first. There is one section that we are skipping though. And so yeah. So we're jumping straight to 8.8. This is improper integrals. And the last two problems on the bonus were what we're asking about improper integrals. And so now hopefully, you'll see how to do those if you don't already know how to do them. So let's actually continue. So let's first talk about what an improper integral is. So this is very important for you to know. And it's very important for you to know why you even care about things like this. So the fundamental theorem of calculus, everyone knows that from Calc 1. It tells us how we compute a definite integral, the integral from a to b of f of x dx. However, you will notice that in the statement of the theorem for the fundamental theorem of calculus, you are assuming that the function is continuous on the interval ab. You're also assuming that the interval ab is of finite length. It's some length that you can actually dissect into n subintervals, right? So these were two very important assumptions under the fundamental theorem of calculus, and the fundamental theorem of calculus, as stated, only holds if these two things are in place. And so you might wonder, what if some of these assumptions are not in place? What if this actually is not true? Then you get what is called an improper integral. Okay, so that's what it's called, an improper integral. So it's going to be an integral under which the assumptions of the fundamental theorem of calculus are not true, not necessarily. Specifically, it means these three things. It means you can either have an interval, you're integrating over an interval of infinite length, which means your lower limit can be minus infinity and or your upper limit can be positive infinity. So that's one thing. And then secondly, you can assume that your function is not continuous everywhere on that interval. More specifically, if you find that the function is discontinuous at a finite number of points on the interval, then we call these three things make up an improper integral. So an improper integral is simply something that looks like a definite integral, but technically it does not fulfill the requirements of the fundamental theorem of calculus. So we have to be a little bit careful in how we evaluate it. So if our function is not continuous on the interval, or if the upper limit is minus infinity, or if the lower limit is infinity, then you get an improper integral. And we'll go over many examples here, but as you might recall, one of the bonus problems, I asked you to evaluate an integral that looks like this. So example from quiz. Actually, to integrate from 1 to 4 of 1 over x minus 2 dx, I believe. And you should have noticed, hopefully you noticed if you knew about this topic, that that is actually an improper integral, because you notice that the function 1 over x minus 2 is not continuous on the interval going from 1 to 4. So while some of you might have thought, whoa, well, I can integrate that to get ln of x minus 2, and then I can plug in the 4, I would get ln of 2 minus plug in the 1, I would get ln of minus 1. That's going to give me 0. And so the answer is probably ln of 2, which you can write it with or without the absolute value since 2 is positive. However, that would be incorrect. Okay, that is what you would do, right? And that's what you would do if the fundamental theorem of calculus applies, because that's how the fundamental theorem of calculus tells us to evaluate integrals. Find the antiderivative, plug in the top limit, minus plug in the bottom limit. It turns out that scenario, that strategy does not work for this integral. This integral, in fact, does what we call diverge, meaning it has no answer, meaning if you were to look at this in the sense of an area under the curve, the area is actually infinite. It doesn't actually make sense for it to be a finite number or any sort of number. So now we're going to talk about how you actually compute these guys. So first of all, identifying them is important. It's when one of these three things happen. Perhaps all of them can happen. So if your function is not continuous on the interval of integration, or your lower limit is minus infinity, or, and these should be and or your upper limit is infinity, any one of these things make the integral that you're looking at an improper integral. And why is it an improper integral? Why does it not make sense to actually do this? Is, again, the fundamental theorem of calculus says that we need to be able to plug in our limits into our function at a certain point. Oh, 1. I'm gonna drop 1. So normally during a regular semester, someone asked how many quizzes do I drop? Normally during a regular semester, I would drop 2, but because it's the summer, I'm dropping 1. We have half the time. Okay, so when we have a definite integral where the function is discontinuous, or the upper limit is infinity, or the lower limit is negative infinity, we get what we call an improper integral. Now, how do you deal with improper integrals? The issue with improper integrals is the plugging in factor. The thing is, you can't really plug in a number that is going to make your function undefined. So there's going to come a point where your Riemann sum is just not going to make any sense. As well as infinity isn't really a number that you can actually plug into a function and get a meaningful answer, right? So the question is, how do we deal with these improper integrals? How do you actually compute them? So before talking about why they're important, let's actually just talk about, okay, this is a thing that exists. Here's how we actually deal with it. But they are actually very, very, very important objects. Okay, so when you're faced with an improper integral, here's how you're going to approach it. First, you want to identify the bad points. And that is not an official or sanctioned term. That's just what I call it. So that's like a Jhevon term I mentioned here. It's just a Jhevon term. Okay, so the bad points are the points that make one of these three things happen. Okay, so a bad point can be A if it happens to be negative infinity. A bad point can be B, the upper limit, if it happens to be infinity. Or a bad point is any number in between A and B, any x value, any input value between A and B that makes the function undefined. The first thing you want to do is to know that you're looking at an improper integral. and you need to know why the thing is improper. Is it improper because the upper limit is infinity, or the lower limit is negative infinity, or there's a point on this interval where the function is undefined? So you need to identify all of these points, identify when these things occur, okay? Now, the second thing is, you're actually going to break up the integral if necessary. It's not always necessary, but the point is you need to expose these bad points. If you look at this example here that was on the quiz, the bad point here, quote unquote, would of course be x equals 2. Because if x equals 2, you divide by 0 and you're not continuous. However, notice that 2 does not show up on the interval. The 2 is kind of hidden from view, right? The 2, which is the bad point, is between the 1 and the 4. The thing is, we don't want that. We want the bad point exposed because we want to make sure that we tiptoe around it and to make sure that we're not doing anything too crazy. So the first thing you want to do is identify the bad points, and you want to expose them if they are there. So in other words, you want to break up the integral so that you expose the bad point. And you want to expose one bad point per integral. That is important. Okay? So you're going to expose the bad points that you've identified. And you can expose that with, this is a rule that you learned from Calc 1, that you can break up an integral like that. The integral from a to b is the same as the integral from a to c, plus the integral from c to b, where c is any other point on the interval, right? So that you would have seen in Calc 1, and you can use that rule to actually break up an integral into several pieces. So for example, this is an integral from 1 to 4. I know that x equals 2 is the bad point. I can break this up into an integral from 1 to 2, plus an integral from 2 to 4 of this function, right? So that's how we use this, right? And you want it to break up such that there's only one bad point per integral, because in step 3, we're going to use limits to approach the bad point. And you can't have a two-directional limit at the same time, right? So we're going to approach the bad points from one direction at a time and inch closer and closer to it to see how the Riemann sum is going to behave or how the integral is going to behave. So we're going to expose the bad points. We're going to replace them with some random variable, and we're going to let the limit of that variable approach the bad point, and we're going to see what happens, right? So that actually brings us to step 4. Here we're going to integrate in the usual way. Then we're going to take the limit approaching the bad point and see, does the overall answer approaches something? Now, if your overall answer after doing this approaches a number, we say that the integral converges to that number. If you take the limit and the limit goes off to infinity or minus infinity, or the limit does not exist, you say that the integral diverges. So we can talk about an improper integral converging, meaning that when I go through this process, I actually get a real number as the answer. I get something that can be interpreted as quote unquote area, versus the limit misbehaves, either does not exist or shoots off to infinity or minus infinity. In that case, we say that the integral diverges. Okay. And that is also some language that you would have seen in the bonus problem. Okay. Now, it turns out, and we're not really going to mention it here, but convergent improper integrals are actually insanely useful. There are so much applications for them in physics and engineering, in probability and statistics. There are many things that we define in terms of improper integrals. And there are many tools to solve all sorts of exotic math problems that are done by using improper integrals, right? So a lot of you are in an engineering program. There's going to come a day where something called the Laplace Transform is going to be your best friend when it comes to solving differential equations. It turns out that that guy is an improper integral, for example. But it's all over the place, right? And I'll probably mention a thing here or there, but the application isn't really what we care about here in Calc 2. We care about identifying improper integrals and actually evaluating them, okay? And determining whether they converge or whether they diverge and what they might converge to if they converge. Okay, so that's essentially it. That's the process. An improper integral is one where the fundamental theorem of calculus breaks. That means one of these 3 things or some things among these 3 things happen. Once you identify that one of these 3 things or several of these 3 things is an issue with an integral, you are going to identify where all the issues happen. You are then going to break up the integral if necessary so that the problem spots are exposed on the limit somewhere. Either it's going to be an upper limit or a lower limit, but you only want one of those guys per integral. Then you're going to use limits to approach the bad points. So you are going to integrate as usual, apply the fundamental theorem of calculus, and then take a limit afterwards. Then you're going to make a conclusion. Does this integral converge? Does it diverge? Right? So it's a 4-step process to do an improper integral. Okay. So let's actually do some examples. So here, I don't want to do like full examples for everything because, you know, it's going to take a lot of time. So what I'm going to do is I'm going to do some examples where we kind of do half the problem. And then I'm going to give you some examples where we go through some full problems. Okay, so let's move this to the side. And we are going to do these. So here, what I want you to do is just the first part. Do up to step like 2, okay? So I want you to identify the bad points, and I want you to break up the following integrals, okay? Just practice doing that, all right? So what do you think here for this integral here, the integral from 1 to infinity of 1 over x? What is the bad point here? Okay, 0 and infinity. So notice here, our b equals infinity. That's a bad point. You can also notice here that note x equals 0 makes f of x equals 1 over x undefined. But we're not on an interval that contains 0. So it's not a bad point for us. I mean, in general, it's a bad thing if the denominator is 0, but we're not in a situation where that is even a concern. So yes, you should actually consider that, but then you need to notice, oh, yeah, it would be a bad thing if that is actually true, but we don't actually care. So the bad point has to be on the interval, right? So if you look at the definition I gave you, it's discontinuous at finitely many points in the interval AB, right? So we're only concerned about what's going on within the interval, okay? So here, 0 is a bad thing to happen, but we're not in the situation because we're at x equals 1 or larger. However, b equals infinity is the bad point. Okay. So notice here, the bad point is already exposed. So we don't really need to break anything up technically, right? Exposed means it's visually within view. There's only one bad point, and I can already just see him on the interval. So we don't need to break anything up. Now this is going to come up in a little bit. So what I'll do is let's just be a little bit preemptive here. Here's what step 3 would look like, even though we're really focused on the first 2 steps. So the third thing you would have done is notice that the bad point is an infinity. What you're going to do is you're going to approach infinity with a limit. How do you actually approach infinity? Well, you're going to take a limit and you're going to make up some letter. It doesn't really matter what it is as long as it's not a variable that's currently in use. So something like n approaches infinity. You're going to look at the limit from 1 up to n of 1 over x dx. And what you're going to do is you're going to compute this limit here. Just pretend the lower limit is 1 and the upper limit is some number we call n. Apply the fundamental theorem of calculus to that guy. And then what we're going to do is we're going to take the limit as n approaches infinity of whatever the answer is. And then we're going to check, does this actually make sense? Okay, so this was the bad point. So b equals infinity is the bad point. No breakup necessary. Okay, so that's all I want you guys to do here. We're going to worry about the other guys in a little bit. Okay, let's all right, what about this one? Negative infinity, 0, and infinity. Okay, so here you recognize that the bad points. Well, my a is negative infinity, my b is infinity, and x equals 0 is going to make the thing undefined, and 0 is a number that's between negative infinity and infinity. So this guy has 3 bad points. So 1, we identify the bad points. Now 2, of course, now you actually need to break things up, because, so we're going to break things up, because we want to expose all the bad points. Okay, so what is that going to look like here? How do you break this up? Negative infinity to 0. Plus 0 to infinity. Okay, that's a great first guess. Not completely correct though. So here's the what's actually wrong. Where Okay, so here, uppercase. You want to break the integral up so that there is 1 bad point exposed per integral, right? So now if I gave you that additional information, how would you fix this? Because notice here, the negative infinity is a bad point, and the 0 is also a bad point, which means this integral has 2 bad points on the limits. You want to break things up so that there is only 1. Because ultimately, remember, we're going to want to apply limits. I can't have a limit going to 0 and simultaneously going to negative infinity. I want to only be able to do that 1.
Professor.
Yeah.
Could you use the limit of as n goes to 0, and so you would change the 0 for an n?
Yeah, but we're currently not done with the breakup part yet. You'd want to break things up before you start to see where the limits go.
Okay.
But yeah, as the suggestion was made here, go from negative infinity to negative 1. Then you would go from negative 1 up to 0. Then you would go from 0 up to, I guess, 1 if we're following this pattern. Then you would go from 1 to infinity. Right, so we can break it up into 1 over da da. So here, notice on the first integral, this is the bad point. There's 1 bad point exposed per integral. This one here, 0 is the bad point. That's 1 bad point per integral. Here, 0 is the bad point. That's 1 bad point per integral. Here, the infinity is the bad point. And so no, we can't go from -1 to 1, because 0 would be in there and the 0 would be hidden. So that's why an integral from -1 to 1 would also not work, right? So 0 is a bad point. He needs to be exposed. You want to expose all the bad points, but you want to do it in such a way that there is only 1 bad point per integral. When it comes to the -1 and the +1, it doesn't even actually matter, right? So the -1 and +1, the guy that you see here and the guy that you see here do not have to be chosen. any point in the interval minus infinity to 0 and 0 to infinity, respectively, could be chosen. Right, so I could have done negative infinity to minus 17, then minus 17 to 0, and then continue like that. You can pick random numbers. So there's nothing special about the minus 1 and 1 here. You just want to break it up into such a way that there's only one bad point exposed per integral. After this, the third step would be approach each of these using limits. And as you'll see in the step here, as I mentioned here, did I say that? Right, replace them with other variables, right? So you're going to use multiple variables. So each guy here, once you start to actually go about computing these, you're going to use a different variable to represent each of these bad points. So again, N, M, O, P, or whatever. Take a limit as the N is approaching this, etc. Okay, but this is the first thing you need to do. Break these guys up, identify all the bad points, expose them so there's one bad point per integral, and then you can start to worry about, let's apply limits, let's do the integration. We'll do some examples of that, but now I just want you to practice seeing them and breaking them up. This guy. Identify the bad points and break it up. Bad points. 0. Right. X equals 0 is the only bad point. How would you break it up? Go from minus 1 to 0 of the function plus 0 to 1 of the function. Right, so there is one bad point on that integral, there's one bad point on this integral, and all bad points are exposed. Okay, so we're good. And again, this is not a fully worked out example, but we'll do some other examples where we fully work something out, and I'll talk about what the answer means in a little bit. What about this one? So this is actually very similar to what was on the quiz. Just different upper and lower limits. Bad point is 2. And the breakup would look like, okay, 0 to 2, and then you can go from 2 to 3 of this function. That's it. And so now you see 2 is the only bad point. He's exposed. Okay. And eventually, maybe I might even look at the quiz problem and show you guys what you would say is the answer to that one. Okay, what about this guy? This is an improper integral. Why is it improper? Identify the bad points. Right. So some people only had one of them. Be aware here, there are actually 2 of them. So this is obviously undefined when the denominator is 0. You set x squared minus 1 equals 0. There are actually 2 answers, plus or minus 1. You can also notice that this is minus 2 to 2 of 1 over x minus 1 times x plus 1. So there are 2 possible bad points here. X equals 1, x equals minus 1, and Abdul Rahman already gave me the breakdown here. So we can go from minus 2 to minus 1, plus minus 1 to 0, plus 0 to 1, plus 1 to 2. So Here is a bad point, the -1, only one exposed. Here is a bad point, the 1, only one exposed. All bad points are exposed and there's only one bad point per integral. So yeah, this looks good. Okay, so this one would break into 4 parts. Okay, what about this guy? 5 is the bad point. Yes, I know there are no real bad numbers, quote unquote, but that's just what I call it. So 5 is the bad point. And it's already exposed. There's only one bad point. There's no need to break it up. So no breakup necessary. This guy. Okay. All right. So I think we got this. The bad points are your A is -infinity and your B is infinity. And those are the only two. E to the -x² is actually continuous for all other x values, for any finite x value. So you would break this up into, say, -infinity. You can pick a random point between the two. So why not 0? And that's that. And I think we had all those examples. All right, so that's how you identify an improper integral and how you want to actually break it up. Now let's actually do some full problems here. I see them over here. So evaluate the improper integrals or show they are divergent. Okay, so that is what we're going to do now. That is the second example. So these, we're going to fully work out these problems. Boom, 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 boom. Okay, all right. Go. Someone tell me what you think we should do here. Bad point. Infinity. Any others? Okay, that's the only one as far as we're concerned. 0 is not a bad point in this case because we're not on an interval that includes 0. So we are on an interval from 1 to infinity. 0 is over here, right? So he's not in the interval, right? So the only bad point is on, so we're only care about over here, right? So it's already exposed. So there's nothing to actually break up. What you do now is you let a limit approach that guy. So limit as, say, n approaches infinity of 1 up to n of 1 over x² dx. And now what you're going to do is you're going to work out what this integral is. Yeah, it's easy to catch. Yeah, this is what you have to worry about, those multiple choice problems. It's going to be easy to catch you on something silly if you're not paying attention. So be careful. Okay, so how would I actually integrate 1 over x² dx from 1 up to n? How do I integrate 1 over x squared? What's the integral of 1 over x squared? It's ln of x squared, right? Yeah. It's actually minus 1 over x, right? So it's not ln of x squared, right? So you'd think of this guy as x to the minus 2, add 1 to the power, divide by the new power. Now you're going to pretend that you're applying the fundamental theorem of calculus, even though technically you can't really do it. We're applying the fundamental theorem of calculus, so I write 1 up to n on the bounds here. Then I'm going to plug in the n minus, I'm going to plug in the 1. Okay. So notice what happened here is 1 ID bad points, right? And in this case, it was that guy. 2 set up breakup if necessary, and set up limits to approach bad points. 3, evaluate the integral as usual. So you just pretend that the fundamental theorem of calculus holds and you go through the integral. Right? So that is what we do. And now here, step 4, finally, find the limit at the end. And what is the limit of that? What is gonna be the answer here? Limit as n approaches infinity of this guy. Right, it's actually going to be 1. So 1 is the answer. So what we would say here is we would say answer, the integral 1 to infinity of 1 over x squared dx converges. And in fact, you can include the statement converges to 1, right? But people, you may or may not want to put that. It's going to be 1. How's it 1? Because as n goes to infinity, 1 over n goes to 0. And the limit doesn't affect this because there's no n in it. So yes, you need to review your limits. So this guy converges to 1. That would be the answer to this problem. So does this integral converge? Yes, it does. In fact, the integral converges to 1. Right? Now, what does that mean? Well, essentially, if you look at the function f of x equals 1 over x squared, right? So you are having, boom, boom. So that guy looks like this. And that, right? That's your f of x equals 1 over x squared. What we are basically saying here, according to what this integral is saying, is if we start at the point 1, and we look at the area under the curve from 1 until forever, like never actually stop, find all the area under this curve to the right of 1, it turns out the area here is 1. So it might seem like there's going to be an infinite area here, but it turns out there isn't an infinite area. The area under the curve is actually going to be finite. And this might seem crazy to some of you, like, what do you mean the area is finite? It goes on forever. Yes, the area here is finite. Now, there are many ways that you can look at this. You can pretty much say, well, no matter how much I add on to the area, we will never exceed 1. And at the same time, at any point that I haven't gotten to 1, I can still add on more area to get closer and closer to 1. So the area here is always approaching 1. And we know that it is going to be larger than anything that is smaller than 1. And at the same time, it's never going to be bigger than 1. And from our perspective, what this means is that the area is 1. And this seems like very counterintuitive sometimes, but it's actually what the answer is. And it actually is useful that we're able to find such an answer. But I think there are going to be problems in your homework that actually explores this, or at least I hope. There are all sorts of things that are kind of strange in this regard. So for example, I believe there's something called Gabriel's horn, which is when you look at the integral from 1 to infinity of 1 over x dx. And it turns out that that is a guy that has finite surface area, right? So Gabriel's horn, so here's a crazy example. Crazy, famous example. I believe it's called Gabriel's horn. So it's if you take f of x equals 1 over x and rotate about x-axis. So this gives you, you have this kind of x positive. And you kind of rotate this guy about the x-axis for x greater than or equal to 1. So you start this at 1, and then you rotate it around. And what you actually get from doing that is you create this sort of horn that's of infinite length. And it turns out that you can actually compute that this is a horn that is actually going to, if you try to find the volume of that, the volume that is contained within this horn, it turns out that the volume is infinite. This will have infinite volume. However, if you try to measure the surface area of the horn, it turns out that that would have finite value. In other words, you can take paint and paint this horn, but you can never have enough paint in all the universe to actually fill the horn. Which is crazy, but it's actually true. And you might say, well, how is knowing that useful? Well, it turns out it's going to be useful in a class beyond this. Unfortunately, we don't go into applications for these guys. Yeah, it's crazy. But that is actually a pretty interesting example, right? It does sound very, very philosophical. The name probably has something to do with Gabriel's horn. It has this very ostentatious name. But yeah, you have situations like this where it's weird that you can actually get answers for certain things, and there are certain things that you might think the answer is infinity, or there's no way this is going to make sense. But then you start to use integration and you apply it as an improper integral, and you start to get all these answers coming out of the woodwork. And there is going to actually be some meaningful answers to questions that themselves don't really seem meaningful. And it turns out that questions like these and their answers are actually useful in real world applications. Oh, I believe Gabriel is not the name of the person who figured it out. Gabriel is supposed to, I think that's a religious connotation, like the angel Gabriel. Right, you know, one of those angels that they're always writing in a picture that he's around God and he's blowing a flute or whatever. I think it has a religious connotation. I don't think it's named after a mathematician. It's a biblical reference. Right. You know, you always have those pictures of the angels blowing flutes or trumpets or whatever. Yeah, so they named it after this, right? And there's like, this is the angel's horn, and hey, you can paint this horn, you can paint the surface of this horn, but you can never actually fill it up with paint. Separating church and state since 1962. Okay. All right. So that's what it's called. It's an infinite horn, but you see things like this all the time. So there are going to be times when you're looking at something like this and you're like, why would this even be something we're looking at? Obviously the answer is not going to make any sense. And then you realize, nope, the answer actually does make sense. It turns out that there is some meaning that we can assign to this concept that might at first glance seem absurd. And it's actually surprisingly useful. And some of you will see some uses of this in, I want to say, differential equations is probably the first place that you're going to start to see things like this being useful. But yeah, it's an interesting example. This is very similar to Gabriel's horn. And in fact, this one, if I did Gabriel's horn with 1 over x squared, that would actually have both finite volume and finite area. So that's some food for thought right there. Okay, so let's look at this one. Okay, so bad points. Infinity and 0. Right, so here, both infinity and 0 are bad points. What do? Right, break it up. Can go from 0 to 1, and then we can go from 1 to infinity. So can go from 0 to 1 of this guy, go from 1 to infinity of that guy. Okay, what we do now is we let limits approach the bad points. So let's say I let n goes to 0 of n up to 1 of 1 over x squared. Plus, you want to use a different guy. You want to think of these two limits as being different things, because you don't want this, the Riemann sums of this guy interfering with the Riemann sums of that guy. So use two different limits, right? So use different variables for each integral. Okay, so I use an m here and I use an n here. And in fact, I can even be a little bit more precise with this n equals 0, because remember, limits are also in and of themselves fickle. You can have a limit coming from the left and a limit coming from the right, and they both have to agree in order for the limit to exist. And it turns out that there are times when you don't actually need all of the angles or all of the directions. Here in particular, if we're approaching 0, where are we approaching it from, the left or the right? Because this can actually make a difference in whether or not the limit is actually going to give us an answer. Okay, so it turns out for this one, we need from the right. Right. So why? Look at the interval that we're looking at. So this is 0. We're looking from 0 to 1, and then we're looking from 1 to infinity. Now, you always approach infinity from the left. So that's not even, you don't even say that, right? Approaching from the left. Always for infinity, right? You always approach infinity from the left. You can't be on the right side of infinity approaching infinity. So we don't even write it. However, if you're on this interval, it means that you are filled in. You don't care what's going on over here. You only care about what's going on over here. So if you're getting close to 0, you're approaching from the right. The 0 is the guy that's on the left. So if you're going to the left extreme, you must be approaching from the right. Right? Because the 0 is on the left, right? The 0 is to the far left, which means everything that's in your interval is to the right of the 0. So you're going to be approaching 0 from the right. Now that can make the difference between a limit working out and not working out at times. So you might want to actually get a little bit more specific with your limits. There are times when it won't actually matter whether you're approaching from the right or to the left, but it can actually matter in some situations. In fact, we already know how this guy integrates. This guy integrates to -1 over x. And now -1 over x is one of those guys that if you're approaching 0 from the left or from the right, it actually makes a difference, right? So the limit as x approaches 0 of 1 over x does not exist. However, the limit as you're approaching 0 from the right of this guy, we define that to be positive infinity. The limit as you're approaching the left of this guy, we define that to be negative infinity. So at the end of the day, this is going to be -1 over x, and we're using the limit as n approaches. N approaches 0 from the right of this guy, where I put there's an n here and there's a 1 here, plus I have the limit as m approaches infinity of -1 over x between 1 up to m. Okay. So here I'm going to plug those guys in. Limit n approaches infinity from the right, and I'm going to have -1 plus 1 over n, and I'm going to find that limit plus the limit as m approaches infinity. I'm going to have -1 over m plus 1, and I'm going to find these limits. Now, what is the first limit? The limit as n approaches infinity, as n approaches 0 from the right of this guy. What is that limit? No. No. N is approaching 0, right? It's approaching it from the right side. Right? Remember, you have the function y equals 1 over x. Looks like this and that. If you're approaching 0 from the right, what happens to the y values? The graph goes up. Y is approaching infinity as x is approaching 0 from the right. Right? So this is actually positive infinity here. Now, here's the thing. This diverges. And here's something that can actually save you a lot of time. Once one of the limits diverge, yes, you really need to review your limits. That's actually a very important thing. It's good that you're noticing it now. So I guess we all know what we'll be working on tonight. go back to your 201 notes or my 201 lectures and review all your limits. So now here's one pro tip. Once one of the limits diverge, and I'm pretty sure I typed this up in the notes, but I typed the notes a while ago, so I don't remember what I typed. So let me just write it again here. Once one of the limits diverge, the entire improper integral diverges. So this is a very common error that students will make. Sometimes they're like, okay, this limit over here is not going to behave, but maybe if I do some of the other limits over there, they're going to kind of cancel each other out. It turns out that that does not apply to the theory here, right? There's no such other thing. So it's not like, oh, I have a positive infinity here, so hopefully one of my other limits can be negative infinity, that they cancel out, because that does not work. Remember, infinity minus infinity is an indeterminate form, right? Once one of your limits diverge, the whole thing diverge. That is actually a very important thing. It's worth me writing down again. Once any one limit diverges, the whole integral diverges. So you don't have to work out, you don't need to work out all of them. So there are going to be times where you're going to be doing a problem and you're going to kind of spot with your eye, especially if you're very good at limits, you're going to be able to spot with your eye, hey, here I have a list of 5 integrals, but I can see that the third one is not going to work. What you can do is you can just work out the third one and show that it does not exist, and then you don't have to work out the other 4. So that's going to save you a lot of time. You can work out the third one and be like, okay, this guy diverges, so the whole problem diverges. So that's going to be a great time saver there, right? So each integral has to stand up on its own merit. Okay, now I do want to point something out. What does this mean? I want to actually compare this to the last one. So here, notice that in example A, we had 1 over x squared. We started at 1, went on forever. And this here, area was finite. In this example, so example A versus example B. Notice what happened here. I had the same graph. The difference is I didn't start from 1, I started from 0. Here, the area is infinite. It's the same f of x, right? So this guy's f of x equals 1 over x squared. This guy's also f of x equals 1 over x squared. So what does this actually mean? This means that this part of the area is infinite. Okay. And now what you'll realize is that at that left endpoint, what's actually occurring is a division by 0. And it is so hard to overcome a division by 0. Everything breaks down once you start dividing by 0. That's one thing, right? So this guy, he can overcome extending for infinitely long. However, he cannot overcome the fact that, hey, we're getting close to dividing by 0 over here. This guy, this here shooting up towards 0 causes way too much chaos to overcome for this guy, right? So this guy is actually, in this case, we have finite error. In fact, it's a very relatively small finite error, 1 squared units. However, if I just attach the area that's in the portion between 0 and 1, that's actually an infinite amount of area there. So this guy actually diverges, and it diverges because of the portion between 0 and 1. This portion here, we actually already know that it's going to converge. This portion here actually goes to 1. That part here goes to infinity. So there's an infinite amount of area between 0 and 1. However, there's a finite amount of area from 1 to infinity. And in fact, any number I pick that's close to 0 but not actually hitting 0, like 0.0001, there will be a finite area from that point going off to infinity. However, between 0 and that point, you are going to have infinite area. So just some more food for thought there. Okay, so far I think you know all the important scenarios that you can end up with here. So you can have an improper integral that you don't have to break up the limit, the integral, but sometimes you might have to break them up. Once you break them up, use a different letter to approach each bad point. You might have to identify if you're approaching from the left or from the right. You do not have to identify that if you're approaching plus or minus infinity, because you're always going to approach negative infinity from the right, and you're always going to approach positive infinity from the left. So those guys you don't have to identify. But the intermediate points, you might want to identify them because the limits can change their answer based on whether you are coming from the left or from the right. Then another thing you should know is once I actually do the integration, apply the fundamental theorem of calculus, and then take the limits, if any one limit messes up, the entire thing messes up. So you don't actually have to do all the work. If you kind of notice that one of the limits are not going to give you an answer, you can just stop at that point and just say, this is going to diverge. Okay, what about this one? Infinity is the only bad point, and it's already exposed. So I would say limit, I say n approaches infinity of 0 up to n, 1 over x squared plus 1. Now I'm going to do that integral. What is that integral? What is the integral of 1 over x squared plus 1? It's arctangent. So I'm going to plug in the n minus plug in the 0. What's arctan of 0? Arctan of 0 is 0. So this just becomes the limit as n approaches infinity of arctangent of n. And what is that? Right, that's pi over 2. Also something you should know. So here, the integral converges. In fact, it converges to pi over 2. The graph of this guy looks very similar to a very important graph, but we'll get to that guy in a little bit. He is going to look like this. And we just found that this area here, so if this is the graph, y equals 1 over x squared plus 1, then the area here is going to be pi over 2. Of course, it stands to reason that the area on the other half is going to be pi over 2 as well. So the area from negative infinity all the way up to infinity of 1 over x squared plus 1 is actually going to be pi. Let's get another. Now, this isn't quite the graph, but there's a very similar graph to this. Y equals e to the minus x squared has a very similar graph. I shouldn't say very similar, has a similar graph. It looks the same, but it behaves very differently because one is an exponential versus a polynomial, right? Has a similar graph. And is important, muy importante, in probability and statistics. there's something called the bell curve. And it turns out you can create the equation of the bell curve isn't y equals e to the minus x squared. However, it is a transformed version of e to the minus x squared. So when you're doing like a normal distribution, it turns out that the graph of a normal distribution is a transformed version of the graph e to the minus x squared. And then being able to find probabilities for like times extending into the future, extending to infinity, you're essentially finding the area under this curve. And so you can actually find an integral that can compute the area under the curve and hence find probabilities that has to do with normal distributions. And of course, one of the rules for probability is the area under the entire probability density function has to be 1. So it turns out you can actually create a transformed version of this graph such that the area from minus infinity to infinity actually equals 1. And you can actually use this to create to compute probabilities. Of course, that is something that we will see. We'll see a guy like this later. I believe I gave it some other examples with this guy. All right. Let's actually wrap up with this guy. This is an important guy that we will be looking at in the future. So for what values of P does this guy converge? So this is 1 over x raised to the P power, in case you can't see that very well. Okay, so Kayla thinks its P is greater than 1. Now, there are some obvious things that you would point out here. Notice that if your P is negative, then if you have 1 over x to a negative power, it's the same as x to the positive power. Then if you integrate that, the power increases. And of course, if you plug in infinity by taking a limit, that's going to shoot off to infinity. If you plug in P equals 0, you just get 1. Then if you integrate that, you would get x. Then when you take the limit as that goes to infinity, that's going to go off to infinity. Then you might think of, well, things really start to change when your P equals 1 exactly. If it equals 1 exactly, that's 1 over x. The integral would become ln of absolute value of x. And that is going to diverge once the input starts going off to infinity. Then you might start to think, does this ever converge? And it turns out it did, because we did an example earlier where it did converge 1 over x squared from 1 to infinity. We saw that this guy actually had an answer. So we know that there is some answers. And so it turns out that if your P is larger than 1, then when you try to integrate this, you just rewrite it to use the power rule. It will be x raised to a negative power. Once you add 1 to the power is still going to remain negative because the negative power is greater than 1 in absolute value. And it turns out that that guy, you'll actually get it to converge. And so you can actually go through and compute when this guy actually converges. And knowing when this guy converges is actually a very important thing to know. In fact, there's a theorem in our book that tells us about it, but I'm going to actually show you where this comes from. Here, we'll consider cases. We can look at P is less than 0. We can look at P equals 0. We can look at P is greater than 0 but less than 1. We can look at P is 1 because this actually behaves quite differently. That guy gives you an ln. And then we can look at P is larger than 1. And so you can go through. 1, if your P is less than 0. So just for, to make it nice, set P equals minus K, where K is greater than 0. And then the integral from 1 to infinity of 1 over x to the P just becomes the limit as n approaches infinity of 1 up to n of x to the positive k. This is going to be the limit as n approaches infinity of x to the k plus 1 over k plus 1 between 1 and n. You'll notice that when you plug in n, now you'll get the limit as n approaches infinity of 1 over of n to the k plus 1 over k plus 1 minus 1 over k plus 1. And this guy goes off to infinity. And so here diverges. So that guy actually diverges. So let's look at the other case, 2, p equals 0. So if you look in case 2, then the integral from 1 to infinity of 1 over x to the p is just equal to, well, from 1 to infinity of just 1, because you raise x to the 0. And so this is going to be the limit as n approaches infinity of, well, the integral of 1 is just x. This is going to be the limit as n approaches infinity from of n minus 1. And of course, that's going to go off to infinity, so it diverges again. Then if you look at case 3, between 0 and 1, if your p is between 0 and 1, then you look at 1 to infinity of 1 over x to the p. This is going to be the limit as n approaches infinity of 1 to the n of x to the minus p dx. This is going to be the limit as n approaches infinity of x to the minus p plus 1 over minus p plus 1. And so this is going to be x to the minus, well, it's going to be n to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. Now, this you're going to notice, this is a positive number because your p is actually between 0 and 1. So it's something that's smaller than 1. So you have 1 minus p, but that's actually positive. And so now we have infinity raised to a positive power. So it means that this whole thing is going to go to infinity and it diverges again. If you look at the fourth possibility, p equals 1, then you'd have the limit as from 1 to infinity of 1 over x to the p dx. Well, that's just going to be the integral from 1 to infinity of 1 over x dx. Of course, you're going to take the limit here. And that is going to give you ln. So here you're going to have the limit as n approaches infinity of ln of n minus ln of 1. Now, of course, ln of 1 is actually 0, but ln of n, this goes off to infinity, so diverges. And at this point, you're probably losing hope. Is this guy ever going to work out? And it turns out, in our last ditch effort, our hero digs deep, finds a way. If you look at 1 to infinity of 1 over x to the p dx, you would look at this as, say, the limit as n approaches infinity of 1 up to n of x to the minus p. That is going to be x to the minus p plus 1 over minus p plus 1. You plug in the n. Plug in the 1. Now, what you will notice here is that this guy here is negative because my p is larger than 1. So if I have 1 minus p, that's going to be smaller than 0. And so this here goes off to 0. And so it turns out this guy becomes, well, 1 over, well, technically it's 1 minus p, so this becomes p minus 1. Converges. Now, this is actually a very, very important thing, believe it or not. But in the next class, in tomorrow's class, where did I put this? Ah, there we go. This actually leads to a very important theorem. So this guy, I don't know why this is not. Okay, hold on. Okay, there. Okay, so this guy, it turns out, is a very important theorem. It's useful for many reasons, but an important reason that is going to be useful for us is for something called the comparison theorem, which we'll deal with in tomorrow's class. So this is actually something that we should know now. So we all should know this important fact that, so this, you definitely want to have this memorized. The integral from 1 to infinity of 1 over x to the p dx converges if and only if, this guy is if and only if, IFF, it's not a typo. It means if and only if. It's a mathematical statement that works in both directions. I guess I can talk about that next. So it means that if your p is greater than 1, then this guy is going to converge. And if you realize that this guy converged, then it must mean the p is greater than 1. So it's a two-way mathematical statement. And it's actually useful in something that we call the comparison theorems, which we'll cover next time. But that, ladies and gentlemen, is improper integrals. Okay, yeah, so now you know that. I just wanted to show you guys, but we had to discover what an improper integral was for me to show you that proof. Yeah, sometimes it's nice to know where things come from. At the end of the day, even if you don't understand what I just explained, knowing that thing that I just put in a green box is going to be very important. It's going to be a fact that you should be able to use, just know how to state and use at will. Right? We're actually going to use that next time. But for now, we're going to wrap up there. And I will let you guys go. Tomorrow, we're going to do some more on improper integrals, but we're going to look at improper integrals where we can't actually compute the integral. So we can't actually do this part right here, right? There are going to be times when we need that. And the example I mentioned earlier kind of tells you when these scenarios will come up. Here's a very important graph, but we should know that we can't actually know what that is as an antiderivative. So we're going to learn how to look at improper integrals that we can't even integrate. So that's what's in store for tomorrow's class. The quiz is already graded, so it's multiple choice, so it's graded automatically. You should be able to see your grade already. If not, I'll make sure to go and publish the grades right now. But good night, everyone. We'll stop there, and I will see you guys in the next.
Jhevon, I would like to speak to you before the class, after the class ends. Like, I'll speak to you for 1 second.
Okay, I'll send you a link for office hours. Okay. All right. Everyone else, good night. Hopefully that was clear, everything, and we will pick up with that tomorrow.